Aice Physics Motion Review. In this video, I'm going over the reviewing motion questions from the beginning of the semester. I'm going to read each question, organize the information in a data table, and select the best motion equation to answer. Please pause the video after I read each question and try to solve before showing my work. First question, a rocket lifts off from rest with an acceleration of 20 meters per second square. Calculate its velocity after 50 seconds. Please pause this video, try to answer this question. This is the final answer. Okay, so this is my data table, and this is a diagram that illustrates the story. So the initial velocity is 0 because the rocket starts from rest, so it's 0. And the final velocity is the value that I want to calculate after 50 seconds going up with an acceleration of 20 meters per second square. Here we have highlighted all the 4 motion equations. And how do I select the right one? Well, distance was not provided, so I cannot use the 2 and 3. So by elimination, I just have equation number 1 and equation number 4. But equation number 4 is, I can use when the acceleration is 0. In this case, acceleration is not 0. So by elimination, I'm going to use equation number 1. So the substitution here, VI is 0, A is 20, and time is 50, and that's the final answer. The final velocity is 1,000 meters per second, or a Cambridge unit, meter second minus 1. Second question, a train traveling at 20 meters per second accelerates at 0.50 meters per second square for 30 seconds. Calculated distance traveled by the train in this time. And here is the answer. So here is my data table with the information given in the problem. The initial velocity is 20 meters per second. Didn't say anything about final velocity. Is asking for the distance. And the acceleration is 0.5 meters per second square and a time of 30 seconds. Now, based on the data table, we need to select the correct equation. So it's looking for distance. So in my equation, I want distance being included. So which means equation number 2 and equation number 3. So which one? So the problem gives the time. So the best option will be equation 2 because I do have time here. So doing my substitution, VI is 20, time is 30, acceleration is 0.5, time square, so that's the final answer. The distance is 825. Question number 3. A car is traveling along a straight road at 8 meters per second. It accelerates at 1 meters per second square for a distance of 18 meters. How fast is then traveling? And this is the answer. Let me place a comma right here. It sounds better. So here is the data table. VI is 8 meters per second. VF is the value that I want to calculate. Distance is 18 meters. Acceleration 1 meters per second square. And no time was given in this problem. Based on this data table, I need to select the correct motion equation. So here, distance was given. So I'm between equation number 2 and equation number 3. And is asking for the final velocity. So my option will be number 3, which is perfect. There is no time here. So that is the one. With the substitutions, VI is 8 square, 2A, distance 18. So my final answer is 10 meters per second. Question number 4. A cyclist is traveling at 15 meters per second. She brakes so she does not collide with the wall. Calculate the magnitude of her deceleration. Please note the word magnitude means just the absolute value without the sign. But here I wrote as an answer because the calculation is going to lead to a negative value. But it's asking just the magnitude, so we can eliminate this negative sign and say just 6.3 meters per second square. So here I have two things. I have a data table and a diagram representing the story. So the initial velocity of the cyclist is 15 meters per second. The final velocity is going to be 0 because here it says that she needs to stop before collides with this wall. So the final velocity must be 0. And the distance that we need to figure out this acceleration is the distance where when she starts to press the brakes to the time that she stops. So is 18 meters and is looking for the acceleration. To select the correct equation, we need to look at our options and the data table. It's asking for the acceleration. So we have acceleration 1, 2, and 3. So which one? What else we have? We have distance. So we can use just 2 or 3. What else? We don't have time. So equation number 3 is the correct one. We don't have time and we have a distance. Okay, so using equation number 3, you're doing the substitution. The acceleration is negative because it's decelerating, 6.3 meters per second square, and the absolute value here is, which is the magnitude, is just 6.3 meters per second square. Question number 5. A stone is thrown from the top of a vertical cliff 45 meters high above level ground with initial velocity of 15 meters per second in a horizontal direction, according to this picture. How long does it take to reach the ground? And how far from the base of the cliff when it reaches the ground? So basically this question is asking two things. One is the time the stone is going to reach the ground and how far will be the stone from the base of the cliff. This diagram represents the trajectory of this stone from the top of the cliff to the ground. So it's going to form this arc. The reason is because the horizontal velocity is going to be pulling the stone in that direction. This horizontal velocity is not going to be affected by gravity because gravity is vertical and this velocity is horizontal. So it's going to be completely ignored here and we are going to have a constant value from the top of the cliff to where land on the ground. However, vertically, the component that is vertical is going to be affected by gravity because vertical with vertical. So initially it's going to be 0 and as the time goes by, this vertical velocity is going to gain speed with the acceleration of gravity as 9.8 meters per second square. So it's going to land the ground with a greater velocity than by the point where it was from. So it's gain velocity over time. So that's why we have the shape as an arc, because one force or one velocity is going to be pulling that direction, and vertically is going to gain speed and pull downward. So that's why we have this arc. If we didn't have the vertical component, so the stone will be having this trajectory the entire time horizontal. But because you have both components, so one is go horizontal and the other one is going to pull it down to the ground. For this reason, we can separate this motion into two independent motion. One is a horizontal one, at which there is no acceleration. The velocity remains constant the entire time, which you can see here in this data table. The initial horizontal is 15 and the final is 15. The distance, the horizontal distance, is from the base of the cliff to where the stone landed. Acceleration is 0 because there is no change in velocity, and the time that takes from the cliff to the ground, we are gonna call the horizontal time. Now let's take a look on the vertical table. On the vertical table, the initial velocity is 0, the final velocity is a value. As you notice, the vertical here is kind of a free fall. So it's 0 and is going to gain velocity as it stay in the air. So here the distance, the vertical distance, is the height of this cliff, which is 45 meters. The acceleration is the acceleration of gravity. And the time we are gonna call TV, or the vertical time. However, because the stone is going to land at the same time of horizontal and vertical, we can state that the horizontal time and the vertical time have the same value. Following the same sequence, which equation we can use for the horizontal table? So let's take a look in our selection here. So equations 1, 2, and 3, we have acceleration. Acceleration here is different than 0. For equation 4, we do not have acceleration, and acceleration here is 0. So in this case, for the horizontal table, the best equation is this equation right here, or we can derive a formula for distance. In this case, distance is velocity times time. So either one, we can derive any equation from those three variables. In this case, I'm going to write something similar to this one. Because the problem is asking how far from the base of the cliff the stone reaches the ground, I can use this table to calculate this value. So here we have, I just show you the selection of equation. So I have here my horizontal distance is the horizontal velocity, which I have, times the horizontal time. I do not have this value. So we need to calculate this using the vertical table. So I'm looking for the horizontal time, but I know the horizontal time and the vertical time are the same. So which equation am I going to pick here? So definitely not 4, and definitely not 1, because equation 1 does not have distance. So I'm between 2 and 3. If I'm looking for time, I cannot use equation 3 because I don't have time here. So my best option is this one. D is equal VIT plus half AT squared. And I also can use a simplified form because my VI is 0. So this section of the equation is 0. So then I have just half AT squared. My A is 9.8. And half of 9.8 is 4.9. So this is a simplified version of this equation number 2 when the initial velocity is 0. So using this equation, the V is equal 4.9 TV. Notice that I'm using subs here, just subscript, like V for vertical. So my dV is 45, 4.9 TV is square. That's what I'm looking. So my TV is 3.03 seconds. So here we have that since TH and TV are the same, so the vertical time is 3.03 seconds that we calculate here, and then we can infer that the horizontal time is also 3.03. Now that I have this value, I can substitute in this equation to find how far the stone went. So here is 15 meters per second times this time is 45.45 meters. So the answer for this question is time is the mark shows 3 seconds and the distance 45 meters. Question number 6, very similar to question number 5 about a horizontal launch. A ball is thrown horizontally from the top of a tower 30 meters high and lands 15 meters from its base. What is the ball's initial speed or velocity? Here is the answer. Please pause this video and try before showing my work. Okay, here I set up two tables, one for the horizontal motion and the other one is for the vertical motion. Horizontally, like I mentioned before, the velocity is not affected by gravity, so will remain constant the entire trajectory. So initially is VH and final is VH. The horizontal distance is 15, acceleration is 0, and let's call the time horizontal TH. For vertically, my initial velocity is 0 because vertically we see as a free fall. The final velocity, I don't know, so it's VVF. The height or dV is 30 meters. And the acceleration is acceleration of gravity, 9.8 meters per second square. And the time on the vertical is TV. Again, I'm using equation number 4, which is when acceleration is 0. So I'm looking for VH this time. So VH is DH over TH. I do have DH, but I do not have TH. So I need to calculate TV from this formula, from this equation, from this table, to make these equal. TV and TH have the same value, and then I can solve for the initial velocity. So here we have dV is equal 4.9 TV squared. So doing my substitution, my TV is 2.47, which is the same as TH. And then I can calculate the value of the horizontal velocity, which is 6.06 meters per second. Now you are thinking, so here the problem is not asking the horizontal velocity. Not directly. Is asking the initial velocity of the ball. So the initial velocity here is our VH. So that's why we can calculate through this horizontal table. Question number 7. A football is kicked on level ground at a velocity of 15 meters per second, an angle of 30 degrees to the horizontal. How far away is the first bounce? Here in this diagram, I show more details about the trajectory of this ball when it is launched an angle. Considering there is no external factors affecting this symmetry, so I'm going to show you how to solve this problem in a very easy way. First, we need to determine the horizontal and vertical components of this initial velocity. So here is our initial velocity, 15 meters per second at 30 degrees with the horizontal. So then we have the vertical component and the horizontal component. Now, because they are vectors, I'm going to move this vertical component right here. and close this triangle, which is highlighted with yellow. The vertical component is opposite of this angle right here. So I'm going to use sine. Sine of this angle is the opposite over hypotenuse. So here is VV is 15 times sine of 30, which is 7.5 meters per second. Likewise, the horizontal velocity is adjacent to this angle. So I'm using cosine of this angle, which is 30, is the adjacent over hypotenuse. So this is the value of the horizontal velocity, 13 meters per second. To solve this projectile motion, I'm not going to use 15 meters per second. I'm going to use the vertical and horizontal components of this value. Back to the diagram. So my horizontal component of this initial velocity, 13 meters per second, is going to remain constant the entire trajectory as going up and coming down. So VH here, 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 at any point, you'll be 13 meters per second. However, the initial vertical velocity, which is 7.5 meters per second, is going to decrease or decelerate as going up. At the point here, there is going to be 0. On the other side of this trajectory, so the initial velocity here for the vertical will be 0 and is going to increase because now it is at the same direction as acceleration of gravity. So it's going to get higher and higher until land here on the ground. And here is going to be the first bounce. Because we have here two types of motion, one is horizontal, which will not change, and one is vertical, which is changing, we are going to separate this motion into a horizontal and a vertical table. Now, because here I have going up and here coming down, I need to select one of the directions. I cannot use both. So in this case, because you have more information on the initial state of this motion, I'm going to select my vertical motion going up. So here in front of you, you have those two tables. Horizontally is the initial velocity is 13 meters per second. The final, the entire trajectory is going to be 13 meters per second. Even when the ball stops before change direction. And the horizontal distance will be from where kicked to where landed. And the acceleration is 0 because there is no change in velocity. And we are going to call this time, the horizontal time, will be the total time in the air. So going up and coming down. But we are going to call this TH or the time in the air. Vertically going up, so we are going to see just this side of this story. So the initial velocity is 7.5. The final velocity here is 0. So the vertical velocity is going to decelerate until you get to 0 and then change direction. So right here is 0. Your dv here is the maximum height, which is dv, and the acceleration going up because it's decelerating. I personally prefer indicate acceleration negative, 9.80 meters per second square, and the time going up, I'm going to call TV. Actually, I'm going to call T up. That is easy to understand. To select the right equation for the horizontal table, we are going to use equation number 4 because the acceleration is 0. And all these H's that you see here is because I'm referring to the horizontal direction. The objective of this problem is to find the H. So I can calculate VH from this formula because I do have VH. However, I don't have the total time in the air, which is the horizontal time. So I need to go to my vertical table to find the time up, because the time in the air will be the time up plus time down. Okay, so which equation? Well, I don't have vertical distance, so I cannot use equation 2 and I cannot use equation 3. I cannot use equation 4 either because I do have a value for acceleration. So by elimination, I'm using equation number 1. Okay, so equation number 1, VVF is equal VVI plus AVTV. Now remember, this TV here is the time going up. So TV here, I'm calling T up from now on. Okay, so my final velocity is 0, my initial velocity is 7.5. Acceleration is negative 9.8 T up. So my T up will be 7.5 over 9.8. So T up is equal, T up is 0.765. So my TH, which is the time in the air, and the time in the air is T up plus T down. And remember, because the symmetry of this trajectory, there is no external influences. So I would say that T up and T down have the same value. So that will be the T in the air. T up is 0.765 plus 0.765, the same value. So time in the air is 1.53 seconds. Okay, so now to calculate the how far the ball went is DH. VH is 13 times TH, which is the time in the air, which is 1.53. So is 19.88, and we can round to 20 meters. That's the final answer. Okay, this problem is related to distance and displacement. So let's take a look what is this about. A spider runs along two sides of a table. Here is the spider, so that's one side, and this is the other side. Calculate its final displacement. In physics, there is a huge difference between distance and displacement. A distance is the total path traveled by an object in motion. And displacement is the shortest distance between the initial and final point. Going back to the spider story. So the spider runs from here to this corner, and from this corner to the other corner. If the problem was asking instead of displacement, the distance will be 0.8 plus 1.2. But it's not. It's asking for displacement. So displacement runs like this. This is the initial point. This is the final point. So now what we have here, we have a right triangle. So because the displacement here happened to be the hypotenuse of this right triangle, we can use the Pythagoras theorem to calculate this distance. So this distance is 1.2 square plus 0.8 square. So square root both sides. So this displacement is 1.4 meter, which is the magnitude. But usually displacement is related to direction. So how do we find the direction of something like this? So to find the direction, we need to use the tangent of an angle right here. So we can use this tangent of this angle. Tangent is the opposite over adjacent, like this. And the angle will be the inverse of a tangent of 0.8 over 1.2, which is 33.7 degrees. So the correct answer is the displacement of this spider is 1.4 meter at 33.7 degrees. So the direction here is given by an angle. This problem is more common in physics questions. An aircraft is flying due north with a velocity of 200 meters per second. A side wind of velocity 50 meters per second is blowing due east. What is the aircraft's resultant velocity? Give the magnitude and direction. So here I'm showing you all the work that I did, but I'm going to explain from the beginning. So the aircraft is flying due north with this velocity. There is a wind that is making the aircraft shift a little bit its direction. So the wind is at 50 meters per second. So what is the resultant velocity of this aircraft? So I'm using here vectors, representing this velocity going north as a vector, and the direction of the velocity here going east in this direction. The resultant velocity is from the tail of this vector to the tip of the other vector. So this is the resultant that we need to calculate. Because we form a right triangle, so we can use Pythagoras theorem, considering that this velocity now is the hypotenuse. So hypotenuse square is equal to the square of one side plus the square of the other side. So that's the value or the magnitude of the velocity of the aircraft. To find the direction, we need to set the angle here where both tail from the arrow, this arrow has a tail and this has a tail, where both tails they meet. So here is gonna be our angle reference. So now the tangent of this angle is the opposite, 50 over adjacent, which is 200. So angle, they don't have units, so we cancel this out. So the angle is the inverse of a tangent of 50 over 200, which is 14 degrees. So the correct answer is the aircraft velocity is 206 meters per second with a direction of 14 degrees.